Okay, welcome to a very quick video on compound probability. You should have the notes from class. Just kind of quickly walk through some examples here. The big thing here is that when we talk about compound probability, more than one event will be occurring as we think through it. And there's going to be several situations. We'll start off with some basic ideas. Things that you probably could have answered already. Let's say that you have a standard deck of cards. You want to draw a queen. We've probably done this exact question in class already. There are 4 queens, 52 total cards. So your answer here will be 4 out of 52, which reduces to 1 out of 13. That's something where all cards have an equal opportunity or an equal chance of occurring. Something that we've kind of looked at is unequal probabilities. This would be where you roll 2 dice and you add up the sum, or you sum them up, and you see that the probability of getting certain results, certain sums, changes. The numbers like 5, 6, 7, and 8 have a little higher chance of happening than a 2 or a 12. And that's because there's more than one way, or there's lots of ways for the dice to land that would get us a sum of 6 or 7 or 8. So we've totaled all that up. All the denominators are out of 36. But there's just a different number of ways you could get there. So if we want to roll a sum of 4, I just look at the chart here. There are 3 ways for that to happen out of 36 total results that could occur. So we'd get 3 out of 36, which is 1 out of 12. You could have, let's see, a total of 4. You could have a 1 and a 3, a 2 and a 2, or 3 and 1. Those are your 3 options. Okay, we're going to use this chart for a few other examples as well here. So what happens if we think about probabilities that happen in stages? Kind of like what we have been doing in some of our more recent lessons. Now we're going to look at more individual probabilities. So I think a key thing here is to, as you rephrase the question, can you use the word and? So something like, does this happen and then this and then this and then this? If you can phrase it with the word and, that usually means it's something that you're going to multiply together. So in symbolism, you see this stuff up here. I would actually suggest that you copy this down because if you do phrase it with the probability that A and B, these 2 events have to happen, then we're just going to find the individual probabilities and multiply them together. And then one other thing we want to notice is, are these independent events, meaning what happens early on in the problem, does it change what might happen later? That's going to be dependent. Independent it means that it doesn't matter what happened first. It's the typical results. It's going to stay like that the entire situation. So I'll try to give you a few examples of that too. So in our example here in number 4, it says find the probability of rolling a sum of 4 on a single roll of 2 fair dice, and then rolling a sum of 3. And you notice I automatically use the word and. So that means that we're going to be thinking of these things in stages. Now you're going to roll the 2 dice, sum them up, pick them up, roll again. They are independent of each other because what happens on the first roll is not going to change what could happen on the second roll. So you go to your chart and you notice that the probability of a 4 happening is 3 out of 36. Probability of a 3 happening is 2 out of 36. You write those 2 fractions down. You're going to multiply them together and then simplify. You get 1 out of 216. You could also look at this and say, well, 3 and 2 get me a product of 6. And I know that 6 could cancel out with something here in the 36, leaving 1 out of 6 right there. So 6, that's right here, times the 36 that we have left untouched would get us to that 216 right away. So there's lots of ways to simplify the fractions here. Example 5, let's pretend that you have a box of chocolates. There's 12 in there. You're going to offer 3 to someone else. They really like the vanilla ones. So they're hoping that they get that kind each of their choices, but they all look the same. You know that 5 out of the 12 are vanilla. We want to know the probability that all of Russell's picks in this case are that type that he likes. Now think about this. This is a dependent event because once he picks one out, it's going to change the numbers that are left for the second and then the third choices. So I'm going to show you some work here. Again, we could say what's the probability that the first one was vanilla, and then the second one was vanilla, and then the third one was vanilla. That is a sign that we're going to be multiplying these probabilities together. So my first choice, I'd have 5 out of 12 options. Okay, and I'm assuming that I'm going to get that vanilla one. So a 5 out of 12 chance, that means that for my second choice, there's one less to pick from, so only 11 options, and only 4 that are left that I actually want, because we're assuming that this one happened. So this would be 4 out of 11, then 3 out of 10. Those are our 3 rounds. The probabilities for each round or for each stage. Multiply numerators together to get 60. Multiply denominators together to get 1320. And then you could simplify to get 1 out of 22. Okay, so that's when probabilities happen in stages. You're going to multiply, and you want to make sure you know if they are independent or dependent. Section C talks about mutually exclusive events. These are events that they can't really happen at the same time. Okay, so they are separate, they're apart from each other. I think a key thing here is, can you phrase it using the word or? Could this happen, or this could happen, or this could happen? Whenever you do that, you're going to be adding the individual probabilities together. So again, I would probably write down this part that's in red right here. The question is, find the probability of rolling a sum divisible by 4 on a single roll of 2 fair dice. So you have to be able to divide the sum by 4. If you think about it, it could be a 4, it could be an 8, or it could be a 12. So what's the probability that we could get a 4, or an 8, or a 12? That's a sign that we're going to be adding. You would go up to your chart there and say for a 4 it's 3 out of 36, an 8 is 5 out of 36, 12 is 1 out of 36. You add them together, so when we add fractions, we have common denominators. That denominator doesn't change. You add the numerators together to get 9, and this fraction would reduce to 1/4. But again, mutually exclusive. It has to be events that are not going to happen at the same time. Okay, so they are separate in their probabilities, and you can phrase it using the word or. Compare that to overlapping. Overlapping means that the events that we're looking at, sometimes they might have things that are actually in common. And it's going to be somewhat similar. You can still phrase it with the word or, but you have to notice that there is an overlap. You have to think through it kind of carefully. So you would still take the probability of A, add probability of B, but then we're going to take away the combined probability that you see right here. Sometimes Venn diagrams can be helpful, and you don't need to know how to do that right now. We probably would do that in class. But again, I think I would write down this phrasing right here. Okay, our last example for this, what's the probability of rolling one die and getting an even number or a multiple of 3? So we can kind of think about this already just logically. You're rolling it once, there are 6 things that you could get. An even number would be 2, 4, and 6. A multiple of 3 would be 3 and 6. So you see that there's an overlap. 6 was mentioned twice. If you take away one of the times that we listed that 6, there's 4 options that I'd be okay with getting out of 6. So in the end, 4 out of 6, or 2/3, should be my answer. What I want to do is show you for more complicated examples that this formula does work. So I'm going to show you all the algebra work, but again, in this case, this is probably one that could be a little simpler. So here's the work. Okay, the probability that it's even plus the probability that it's a multiple of 3, that's P of A and P of B, minus this probability here that it's even and a multiple of 3. Okay, so probability that's even is 3 out of 6. Probability that is a multiple of 3 is 2 out of 6. Notice that these are the same up and down here. Now, to answer this question, you certainly could say, well, if it's going to be even and a multiple of 3, I know that 6 is the only option. The number 6. Out of 6 total options, you could get this 1/6 right here right away if you wanted to. I just wanted to show you that if you think of doing this sort of notation the way that we did in part B, that you would be multiplying these 2 probabilities together, the probability that it's even and then the probability that it's a multiple of 3. And I just want to show you that you get the same answer. Okay, the probability that it's even is 3 out of 6. Probability that it's a multiple of 3 is 2 out of 6. If you multiply those fractions together, you get 6 out of 36, which would reduce to the 1/6 right here. So for complicated questions, setting it up like this might be more beneficial because you won't be able to get to this simple fraction right away. Anyways, once you have these 3 fractions here, common denominators, so 6 is good for that part. 3 plus 2 is 5, minus 1 is 4. We get the 4/6 that we talked about early in the video, which would reduce to 2/3. Okay, that's it for this video. It was kind of a fast run through. Let's talk about it more in class.